Okay, welcome back. And in this next segment, what I'd like to do is take the neural networks, which you already know about, and show how we can use that to develop an unsupervised learning algorithm called autoencoders, and then develop the Sparse Autoencoder algorithm. So, what we've done so far is talk about neural networks as a supervised learning algorithm. And it turns out that in the history of machine learning, throughout the 1980s, most of supervised, a large fraction of machine learning was using neural networks, and a large fraction of it was actually using backpropagation on label data for supervised learning. It turns out that even though that kind of works, neural networks as a supervised learning algorithm also has some disadvantages. One is that it has a maybe large-ish number of parameters you need to tune. So you need to set the learning rate. There was also the weight decay parameter lambda, and it turns out there are other versions of neural networks with even more parameters. Another disadvantage of neural networks is that using gradient descent, it can take a while to train, and gradient descent is also susceptible to local optima. So it turns out that today, there are many people, including myself, that for supervised learning problems would tend to use other learning algorithms like support vector machines that do not suffer from some of these problems, even though of course even today neural networks does have a number of its sometimes very local proponents. But that's supervised learning. And it turns out that some of the most fascinating recent work in machine learning pertains to using neural networks to do unsupervised learning, where the goal is to learn from unlabeled data. And what I'm going to do is to share some of these ideas with you and show how we can use neural networks for unsupervised learning, which is an algorithm that is really now at the forefront, I think, of cutting-edge research. And eventually, we'll talk about the autoencoder algorithm, and this will take us to talk about some of the unsupervised feature learning algorithms, which was what I was hoping to convey with these lectures. So let's get started. So, in what I'm going to do, now, I'm going to talk about unsupervised learning, and so we're going to be given unlabeled examples, x1, x2, x3. Right, so this is unsupervised learning, and I'm going to continue using the online learning formalism as before, and so I'm going to assume that we have an unending or sort of an infinite sequence of unlabeled examples, x1, x2, x3, and so on. Okay? And we've developed neural networks so far as a supervised learning algorithm, and so to train a neural network using backpropagation, we need target labels. But in unlabeled data set, we don't have them. So what we're going to do is create artificial labels yi, and the way we're going to do that is we're going to set the output to be equal to the input xi. Okay? So you create artificial labels that way. And so now you have your unending sequence of labeled examples, where it so happens that your target labels y are all equal to the input vectors. And so what we're going to do in the autoencoder algorithm is create a neural network with exactly one hidden with exactly one hidden layer, and try to learn this function from the x to y. So in other words, we're going to try to learn the identity function, right? Because y is equal to x, and we'd like to learn a hypothesis where the output is as close as possible to x. So here's an example of an autoencoder neural network where, again, these autoencoders the autoencoders I'm going to talk about will always have exactly one hidden layer. So on the left is the input layer, you have a hidden layer, and you have an output layer. And again, the goal is to learn, something is to learn an approximation to the identity function. Now, it seems as though learning the identity function, seems like learning an approximate identity function would be a particularly easy thing to do, right? You just take your input and you output whatever, the same thing as what you got as input. But it turns out that by placing additional constraints on the neural network, we can still get it to learn fairly non-trivial things, and in particular, we get it to learn interesting features. So, for example, in this neural network that I've drawn on the left, we have 6 input units, again, not counting the +1 bias unit. So we have 6 input units, and we have 3 hidden units, again, I'm not counting the bias, and then we have 6 output units. And what this neural network must do, therefore, is take its hidden unit representation of the input and use these 3 numbers, right? So you have 3 activation values written A2I for I equals 1, 2, and 3. So you have 3 activation values. And what the network has to do is try to reconstruct the entire 6-dimensional input as a function of just these 3 hidden units. And what this network has to do, therefore, is learn a compressed representation of the input. Has learned a way to take your 6-dimensional input, compress it into 3 numbers, and then go from the compressed representation back up to this to a 6-dimensional representation. And this is true because we've limited the number of hidden units the network has. As another example, suppose that your inputs are 10 by 10 pixel images, and suppose and so your inputs are going to be R100 or 100 dimensional inputs, and suppose you have only 50 hidden units, and I guess 100 outputs. If you do this, then once again the neural network is forced to learn a compressed representation of the input, where it must compress your 100 pixels into a 50-dimensional representation. It turns out that in some cases this would not be. It'd be very hard to learn a meaningful compression. So, for instance, if your input pixels were IID, say Gaussian random variables, with all the pixels in the image were independent of each other, then it'd be very hard to learn a compressed representation of the image. But in raw images aren't like that. In raw images, the pixels are not independent of each other, and there tends to be some redundancy in images, right? Adjacent pixels tend to be correlated, for instance. And so if you train an autoencoder this way, it will, on raw images, then it will learn a meaningful compression of your image into 50 hidden units and capture some of the redundancies that are inherent in natural images. For those of you familiar with PCA, or with principal components analysis, it turns out that this sort of neural network representation bears a close relationship to the sorts of representations you get by training PCA. Now, limiting the number of hidden units is one way to force the autoencoder to learn an interesting function, even to learn an interesting representation, even though it's essentially trying to learn the identity function. In the rest of this lecture, in fact, what we're going to do with autoencoders is we're actually not going to place a constraint, or we're not going to force the algorithm to learn something interesting by severely limiting the number of hidden units. Instead, what we're going to do is place a different type of constraint on our autoencoder that will also cause it to learn an interesting hidden layer representation. And in particular, we're going to place a constraint on our autoencoder called a sparsity constraint. And so with this sparsity constraint, we will be able to train autoencoders with, say, 100 inputs and 100 hidden units, or even more than 100 hidden units, and 100 outputs, and it'll still learn interesting representations. So let me informally say what the sparsity constraint is, and then I'll formalize it later and say what the algorithm is. Informally, I'm going to constrain the activations of my hidden units to be close to -1 for all values of I. Okay, so recall A superscript 2 subscript I. This is the activation of hidden unit I in layer 2, that is the hidden layer of my neural network. And so I'm going to constrain my hidden layer activations to be mostly close to -1. And this is just an informal definition for that. And again, continuing with an informal definition, I'm going to think of a neuron as active if, or alternatively, I'm going to think of a hidden unit as, quote, firing if its output value is close to +1, And the term firing is again making a loose analogy to neuroscience, where the neurons in the human brain are highly active if we say in neuroscience if it's firing. Don't worry too much about the terminology, and I'm not going to make too much of the neuroscience analogies. But I'm also going to say that the neuron is inactive if A2I, if its output value is close to -1. Okay? And remember, these are neurons that use the tanh or the hyperbolic tangent activation function, and so the opposite neuron must be must be between -1 and +1. And so the sparsity constraint is that I'm saying, right, this constraint, I'm saying that most neurons should be inactive most of the time. Okay? And again, I guess the neuroscience analogy is that if you look in, say, the human brain, really the brain of any mammal, you find that most neurons in your brain are not active most of the time. And so the sparsity constraints is saying that similar to the brain, most of the neurons should not be firing most of the time. Okay, let's formalize the sparsity constraint. To do so, we're going to imagine that as we get our unlabeled examples, right, our unlabeled examples x1, x2, x3, and so on, we're going to imagine that our unlabeled examples x1, x2, x3 are drawn IID from some distribution, from some probability distribution that I'm going to denote by script D. Okay? So drawn independently identically distributed from some distribution, script D. So imagine that these are images drawn from the distribution of what natural images look like. So the constraint that I'm going to impose, the sparsity constraint, is that I'm going to constrain approximately, say, the expected value of the activation to be equal to some target activation value rho. And this symbol here that looks like a lowercase p, this is the Greek alphabet rho. And the value of rho I'm going to set to a value close to -1. So for instance, maybe I'll set to -0.9 for example. Okay? So just to explain what this expectation means, right? I get to choose parameters W and B from a neural network. And I want to choose parameters so that when I draw, or when I sample a new image X from this distribution script D of images, of distribution of natural images, say, I want the expected value of the activation of my hidden neuron to be close to -0.9, say. And this is for all values of I. Okay? So I'm saying that for each of my hidden units, I want their expected activation, and this expectation is over a random image drawn from a distribution of random images, say. I want that expectation to be -0.9. And so the only way for my neural network to satisfy this expectation constraint is if most of the time the hidden units activation had better be close to -0.1. Right? In particular, the hidden units activation cannot be +1 all the time, because if it were close to +1 all the time, then this expectation couldn't possibly hold. Instead, it was output value is close to -1 most of the time, maybe output value is close to -0.9 or -0.8 most of the time, and only on rare occasions can it output a value close to +1. Okay? Alright, that's the constraint. What I'd like to do next is talk about an algorithm for approximately enforcing this constraint. And my algorithm will have 2 steps, or my strategy for approximately enforcing that sparsity constraint will have 2 steps. The first step is I'm going to keep a running estimate, which I'm going to call rho hat I, of that expectation. Okay, so for each neuron I, I'm going to keep a running estimate rho hat I, and just try to estimate what the expected value of the activation of that neuron is. There should be a 2 up there. Okay? So that's the first step. The second step is, on each iteration of stochastic gradient descent, right? Then also going to update the parameters to make the expectation closer to the target value rho, which was minus 0.9 in the previous example, say. And again, rho is a parameter of the algorithm, and usually we set it to a value close to minus 1, right, like minus 0.9. Okay. So the first thing we need to do is come up with an estimate for what the expectation is currently, and then now that we have an estimate of what the expectation is, we can then modify the parameters in step 2. We modify the parameters of the neural network to try to drive this expectation closer to the target value rho of minus 0.9. So let me explain how we do step 1, which is just as follows. So on each iteration of gradient descent, so on each iteration of our learning algorithm, we're going to perform an update to our running estimate as follows. Rho hat I gets updated as 0.999 times rho hat I plus 0.001 times A2 I. And you do this for every I, for each hidden neuron I. Okay. So rho hat, because we are running estimate, and to start this process off, you can initialize rho hat I to be equal to 0, say. It doesn't really matter that much. So here's the algorithm, right? On each iteration of gradient descent, on each iteration of a learning algorithm, we're going to get a new training example, and we're going to run that example through our neural network, and so that would give us, the activation of each of our hidden units, right? AI, superscript 2. And then we're going to update rho hat I, our running estimate of the expected value of A superscript 2 subscript I, using this formula. And these numbers, 0.999 and 0.001, are parameters of the algorithm. They should add up to 1. And there's actually a large range of values that will work. But with this particular choice of values, it turns out that after you run the algorithm for a while, it turns out you can show that rho hat I will become an exponentially decaying weighted average of the activations that you saw for roughly the last 1,000 iterations or so of stochastic gradient descent. So just say that again. It turns out that when you run this update, it turns out that rho hat I will roughly be a weighted average, really exponentially decaying weighted average of roughly the last activation values you saw on your last 1,000 training examples. And so if your training examples are really drawn IID from some distribution, then by averaging over approximately the last 1,000 iterations of the algorithm, you have a reasonable estimate of the expected value, right, of the expected value, your reasonable estimate of the expected value of the activation of this neuron. Okay? So that was step 1. And in the second step of this algorithm, on each iteration of gradient descent, we're going to update the parameters of the neural network to try to make the expected value of the activation of this neuron closer to, say, minus 0.9. And so let me go ahead and explain this second step on the next slide. Oh, and actually, before I move on, I'm going to label this equation, equation 1. So this equation 1 is the update rule for my running estimate for rho hat I. Okay? Later on, I'm going to refer to equation 1. That I'm just referring back to this equation. Alright, now let me do step 2 of how we would update the parameters to make the expectation closer to rho, to our target activation value. So, recall that the way we compute the activation of hidden unit I, that's F applied to, this. Where F is the TAM-H activation function, same as before. Okay? And so let's suppose that for hidden unit I, let's say rho hat I is greater than rho. What this means is that, and then again, right, for this illustration, imagine that rho is a number like minus 0.9, and let's imagine that rho hat is a number like minus 0.7. Okay? So that the rho hat I is minus 1. What this means is that you would like the expected activation of the neuron to be minus 0.9, but currently the expected activation of the neuron is about minus 0.7. So if this holds true, then what that means is that we would like the hidden unit I to be less active, right? Because this, expected activation is minus 0.7. We would like this expected activation to be closer to minus 1, right? Want its output values to be closer to minus 1. And so we would like this hidden unit I to be less active. And so one way to do that is to decrease this parameter b1i. Right? Because if you decrease b1i, then that will tend to decrease the value of this sum. And so the argument into f will tend to be smaller. And if you recall what the tanh activation function looks like, this is what f of z looks like. If the input to f is smaller, then f of z will output smaller values closer to minus 1. And so decreasing, b superscript I, decreasing this term bi will tend to move values further to the left of this part, and it will tend to decrease the activation of this neuron. So that's if rho hat I is greater than rho. Conversely, if rho hat I is less than rho, then what that means is we want hidden unit I to be more active, meaning that we want it to be outputting larger values. And to accomplish that, we can increase this bias term. Okay? Because by increasing bi, that in this sum, that will tend to cause the argument to f to become larger, and so f will tend to output larger values, and that will tend to increase the expected value of the activation of the neuron. So, putting these two cases together, this gives us our update rule. bi gets updated as bi minus alpha beta times rho hat I minus rho. And you do this for every I. Okay. Where alpha, this is our learning rate parameter as before, and beta is an additional learning rate parameter. Okay. And again, for later reference, I'm going to call this equation 2. So when I refer to it later, this equation I'll call equation 2. And I had equation 1 on the previous slide for updating rho hat I, right? These running estimates, that was in the previous slide, and this slide, equation 2, is our rule for updating these bias terms. And alpha, once again, is the same learning rate parameter as we had before, as when we were talking about backpropagation, and beta is an additional learning rate parameter that controls how aggressively we change these bias terms in order to try to approximately enforce the sparsity constraint. So let's just look at this expression and make sure that the signs make sense, right? So in the first case, if rho hat I is greater than rho, right? If rho hat I is greater than rho, then this term will be positive, and so minus positive number, and so we'll be decreasing the bias terms exactly as we wanted. And conversely, if rho hat I is less than rho, then this will be negative, minus a negative number, and we end up increasing these bias terms exactly as we want. Okay? So to summarize our algorithm for enforcing the sparsity constraint, what we're going to do is, on each iteration of our learning algorithm, so on each iteration of gradient descent, we get a new example. We'll call X, Y, Z. What we're going to do is 3 things. First, we're going to run a forward pass, to compute all the activations. one to compute all the activations on an entire network. Having done that, we then use backpropagation, which I'm going to abbreviate to backprop. So use backprop to perform one iteration of stochastic gradient descent. And then finally, using the same training example, I'm going to use, equation 1. This was written 2 slides back, right, to update rho hat I, and use equation 2 to update the bias of these bias parameters of my learning algorithm for each of my hidden units I. And by doing this, again, equation 1 keeps my running estimate of my parameter rho hat I, and equation 2 gives me my running estimate of, and equation 2 is used to adjust the bias units feeding into my hidden hidden layers called neurons, so as to try to approximately enforce the sparsity constraint. So that was the Sparse Autoencoder algorithm, and with what you know now, you should take images or what have you and train a sparse autoencoder to learn a sparse representation of whatever your input is. And what I want to do now, the last topic really, is talk about visualization. And in particular, let's say you've set of images, maybe some of the input, but let's say images, and let's say you've trained a sparse autoencoder on a set of images. What I'd like to do is be able to go back and look at the representation that's learned by your sparse autoencoder and figure out, exactly what functions or what features it's computing of the input. So in particular, if let's see, here's a picture of the autoencoder again, and we've trained it, constraining these hidden units to sparse activations. Again, in this picture, I've shown the hidden layer as being smaller than the input and output layers, but once we're imposing the sparsity constraint, that isn't necessarily the case. But let's say we trained this on a set of images. And technically, we'll actually train this, we'll actually train this on whitened images. So whitening is a pre-processing step that tends to cause neighboring pixels of an image to become a bit less correlated. We'll say just a little bit more about it in the lecture now, but don't want to say too much about it here. But let's say we train this on images or whitened images or what have you. What I'd like to do is, say, pick a neuron, say this one, and try to understand what function this neuron is computing of this input. Okay? And to do this, I'm just going to focus on one neuron. And in fact, let me just pick some neuron I, right, for any one value of I. And what I'd like to do is come up with a way to understand just what the neural network has learned, just what this activation is as a function of the input. Okay? And I'm going to do this focusing on one neuron at a time. Now, in order to visualize what the activation of hidden unit I is doing, I'm just going to recall what this is, that the activation of hidden unit I is given by this formula. And so this is some function of the input image x, and again, just assuming that we're working with images for now, what I'd like to do is come up with an understanding of what function this is computing of my images x. And in particular, I'm going to develop a visualization to help us understand this function better. And my visualization is going to be developed posing the following question of what is the input image, or what input image x causes hidden unit I to be maximally active. I.e., maximizes And in other words, I want to ask, what's the input image X that will cause my hidden layer, my hidden unit to output a value as close to 1 as possible? Now, in order to answer this question, or in order to make the answer to this question meaningful, I actually need to place an additional constraint on the images X that I'm going to entertain. Right? And that's because, if you remember, f is this tangent activation function. Right? So this is f of z, it's a tangent hyperbolic tangent function. And so, by setting x to be large enough, to say plus infinity or minus infinity, depending on the size of the w's, I can make this argument to f as big as possible, and then f will output a function will output a value very close to 1. Right? And so, by setting x to plus infinity, minus infinity, I can get this output to be arbitrarily close to 1. And so, in order to make this question meaningful, I'm going to add a constraint that the L2 norm of x must be equal to 1. It actually turns out you can also say less than or equal to 1. So, and then you get the same thing. But this just prevents us from choosing images with pixel intensity values equals like plus infinity. Right? And so what you can show, I won't show this, but what you can show is that under this constraint, the input image X that maximizes this activation of hidden unit I is going to be given by this formula. And so I'm going to assume that I have an input image with 100 pixels, so I'm going to write this sum as a j from 1 equals 100 for 100 pixels squared times. Okay. So it turns out the value of x that maximizes AI, AI superscript 2, is given by this formula. In other words, you set pixel number j to the intensity value given by this formula on the right hand side. I'm not going to prove this result, but you should prove it yourself. And this is a lot like taking a row of the matrix W and treating that as a vector and normalizing the vector to have norm 1. But I'm not going to prove this with yourself. And so to develop our visualization, what we can do is for hidden unit I, for each hidden unit I, right, or really for a hidden unit I, right, set pixel xj as shown in the equation above. Then we can visualize, or we can plot, what the image xj is. And so remember, these xj's, right, these things are pixel intensity values. So I can ask, let's go ahead and set all the pixel intensity values equal to the value of the image that maximizes the activation of this hidden unit. And what I can do is actually, let's just look at the image when the image has these different pixel intensity values. And so, what I'm going to show on the next slide is, let's see, what I did was I trained a neural network with 100 inputs and 100 hidden units and 100 outputs. And what I did was I picked one specific hidden unit, and for that one hidden unit, I generated a 10 by 10 image that maximizes the activation of that one hidden unit. And what I'm going to show is what that image looks like that actually maximizes the activation of this one hidden unit. And when you do that, this is what you get, where on the left here is a 10 by 10 image, and for one of my hidden units, this is the input image X that maximally activates that hidden unit. Okay? And if you look at this image, this image has a has this sort of black region on the right half and a much lighter region on the left half. And so this hidden unit is maximally activated when in the input image, there's all this black on the right hand side, and the left hand side is mostly lighter colored, say. And maybe there's a little bit of white in the far right. And if you look at this image, what you see really, this is a strong vertical line or a strong vertical edge. And so what this hidden unit is doing is, this hidden unit is maximally active when the image has a strong vertical edge, right down the middle of the image. And when the edge is so that it's light on the left and dark on the right. So what this trained neuron is doing is looking for a strong vertical edge with dark on the right then ends up right on the left. Speaking a little bit loosely, is as if this hidden unit has, quote, invented a vertical edge detector. Okay? Because that's the, and more generally, it turns out that you can interpret this hidden unit as measuring the degree to which the image contains a strong vertical edge. And when the image contains a strong vertical edge, like that shown in the image, the hidden unit outputs a value very close to +1. And when the edge is weaker, when there's less evidence for an edge like what you see on the slide, then the hidden unit outputs a value a little bit less than +1. So what this hidden unit is doing is essentially measuring the degree to which the image has a strong vertical edge. And again, speaking loosely, the algorithm has, quote, invented edge detection, or has invented a specific vertical edge detector. Now, what we can do is take the same idea and apply it to different neurons in our neural network. So I did this for one specific neuron. I actually trained my neural network with 100 hidden units, so I can do the same process 100 times for 100 different units, and for each of my 100 hidden units, I would get a similar 10 by 10 image. And when you do that, what you get is the following result, where here's on the left is 100 images. Each of the images is itself a 10 pixel by 10 pixel image, and what each of these images is the what each of these little squares shows is an image that causes one of my 100 hidden neurons to become maximally active. And what you see is that my different hidden units in my neural network are looking for edges in different orientations and at different positions in the image. So again, speaking a little bit loosely, what this algorithm has done is it has, quote, invented edge detection, and is looking for a variety of edges in a variety of positions and a variety of orientations. And that's pretty cool. So, just to summarize, right, we started off with a neural network that we said we would train on, just raw 10 by 10 images, maybe white images, maybe raw images. And what the algorithm has done is it has, quote, invented edge detection, so that what the hidden units are doing is it is measuring the degree to which different edges are appearing in the image. And so if you look at the hidden unit representation of if you look at the hidden unit representation of the input image, what it's doing is it's representing the degree to which different edges at different positions and different orientations, representing the degree to which different edges are present in your image. And if you think about it, what the hidden units, what the AIs, right, the hidden units do, what that's doing is representing an image in terms of the edges that appear in the image. So via an unsupervised learning algorithm, we now have a way that automatically learns, right, to instead of representing an image by the pixel intensity values, we now have an algorithm that can automatically learn to represent the image in terms of the edges that appear in the image. Okay? And this edge level representation is a higher level representation, or a more abstract representation, or maybe a more succinct representation of the image than the raw pixel intensity values. And as you can imagine, representing an image in terms of the edges that appears in it, is sometimes a better representation or a more useful representation sometimes for tasks in computer vision, object recognition, and so on, than the lower level, pixel level representation of the image. Okay. So, let's see. I should say that, of course, some of these sorts of unsupervised feature learning algorithms, a lot of this is still cutting-edge research, and I think researchers are still very much trying to figure out what works and what doesn't work. But with what you just saw, getting an edge-level representation, you can imagine that there are some applications for which this is more useful than the lowest-level representation. So, just a couple more comments. One is that in most of what I talked about here, I used images as a moving example and talked about applying these ideas to images. More generally, you can also apply these sorts of algorithms to other input modalities, such as applying it to audio data or to text data. And your Sparse Autoencoder algorithm will then try to learn an appropriate representation, for audio or for text and so on. So, just as you can learn to detect edges in images, you can hopefully learn higher level representations as well for audio and text and so on. And I think in contrast to, sort of in vision, right, having teams of tens of hundreds, thousands of people handling features for vision, and in audio, having teams of tens of hundreds of thousands of people handling features for audio, I think it's remarkable that you can have the same algorithm that you can apply to learn useful feature representations for images or audio or text or other things. Finally, in what I've shown today, I only talked about how you go from pixels to edges. And think of this as maybe going one level up the representation hierarchy, right? When you put together pixels, group together pixels to form edges. And it turns out that there are more sophisticated versions of algorithms like these that I didn't talk about, but it turns out there are more sophisticated versions of algorithms as well. They can then sort of repeat this process. So rather than just putting together pixels to form edges, you can then repeat the process and put together edges to form object parts, and repeat that to put together object parts to automatically form models of objects. And so you can get more and more complex representations using more sophisticated versions of unsupervised learning algorithms like these. And when you do that, you can actually often get, you sometimes get features that are very rich representations. You input images, you input audio, what have you. And these feature representations are actually often competitive with many of the hand-engineered feature representations, and sometimes even superior to some of the hand-engineered feature representations. But at least, let's see, so I didn't talk about the more sophisticated algorithms today, but at least with today's lecture, you now know enough to implement the basic Sparse Autoencoder algorithm, which is enough to, quote, invent edge detection and get you, high-level representation of your input than, say, the raw pixel intensity values. Finally, that was essentially all the technical material I had. And finally, I just want to remind you that in addition to this video lecture, this video lecture is also accompanied with lecture notes that you can download from the course website, which gives somewhat more details of the algorithms. And one thing I did not do at all in this sort of lecture was show how you can do all of these computations using efficient matrix operations or using matrix vector operations. And so when you implement the Sparse Autoencoder algorithm, do refer to the written lecture notes, because that'll tell you how to use, implement these ideas more efficiently and come with efficient implementations using linear algebra libraries to do almost all of these things using efficient matrix operations. And finally, I just want to wrap up by acknowledging a few people that helped prepare these materials. Just really thank Hockler and Andrew Sachs, who did a lot of work to help me prepare these materials, and also Honglak Lee. A lot of the materials I presented today were actually based on the research of Honglak Lee. And lastly, I also want to thank Daphne Collar, who provided a lot of the inspiration for the format of these lectures. And so, that's it. That's all I had to say. And based on what you know, you should now be able to go back and implement the Sparse Autoencoder algorithm and have an unsupervised learning algorithm, learn interesting feature representations for images or for other input modalities. So, good luck with implementing the Sparse Autoencoder, and I hope you have fun with that.